So it's late in the afternoon, so energy's kind of low. You've all just had something to eat, so hello. Say hello back. Come on, fill the room. Hello. Okay, great, great. As you probably know by now, we're going to be talking about mutation testing, and it's in mutation testing in Python because I'll be talking about an implementation in Python, but most of this talk is more broadly applicable. It doesn't have anything to do necessarily with Python. I just happen to write a lot of Python code, and that's what I wrote. Here, who has done mutation testing or even knows what it is, just raise your hand. Okay, so not everybody. Good. How many have experience with something like PIT, the Java testing, the Python testing tool? Nobody. Interesting. Okay, because that's the gold standard. Mine is very researchy compared to theirs. I work for and part own 60 North, a small software consulting company in Norway. We're based in Oslo and in Stavanger, where I'm from on the West Coast. Represent. Right, so there's an app. You probably all know about it by now. The only thing you need to know about it is the green smiley face. You can ignore the rest of it, including the questions bit. We'll take the questions at the end. I'm going to try to save time for those. A little bit about myself. This is my world. That orange dot in Texas is Austin, Texas, where I'm from originally. Well, Austin's a great city, right? The University of Texas, the U.S.'s largest university, and the U.S.'s top-ranked public university. It's where I went to graduate school. It's a wonderful place. Go Horns. Austin's a beautiful city, and it's got a real personality to it. It's the best part of Texas. If you ever go to Texas, go to Austin. This is a statue of Stevie Ray Vaughan, a famous guitar player from Austin who died tragically. And this is a statue the city built. And this kind of represents how they feel about themselves. They're really big into live music, rock and roll, blues, that kind of stuff. And it's a really pretty city. If you get a chance, go to visit it. About 7 years ago, I moved to a place that's very different. This is Stavanger. This is Lysefjord from the Pulpit Rock. If you've ever been to Stavanger, you've probably been to exactly that view. It's the prettiest place in Norway, no arguments. We have different kinds of statues there. These are 20-meter tall stone swords rammed in the earth to represent the unification of the kingdoms of Norway hundreds of years ago. About 20 minutes from my house, all this stuff. It's a beautiful place to visit. If you've never been, Stavanger's great. And that's where I founded 60 North a few years ago. So enough about me. Let's move on. Mutation testing. I first heard about mutation testing maybe 2 years ago from a guy named Seb Rose, who if you go to conferences, you may have heard of him. He's a really great speaker. If you get a chance, see him talk on any topic and ask him what he's passionate about. That'll wind him up. He's a good guy. And it was something that resonated with me. Mutation testing, which I'll describe in great detail, resonated with the way I think about programming and kind of just the way my brain works. And I got very interested in it and set about to write some mutation testing stuff in Python, which is the language that I use given the choice. It's a really neat technique. It's kind of researchy, not entirely practical, but I think you'll all find that the ideas in it are really good and something that we should strive to have good tools for. So most of what I'm hoping to do in this talk is to get across what mutation testing is, what are the challenges, and to get you interested in it enough that you might start thinking about it as well and contributing your own tools, contributing to these tools, to the other tools, and making it a better ecosystem, because that's kind of where we are in the world with mutation testing, I think. So what is mutation testing? You start off with two premises. You have your code under test, your application or your library, whatever. It's code that is presumed to work. And you have a test suite that you presume fully tests the functionality of that body of code. You then introduce a single controlled change, and we'll discuss these in a fair amount of detail, but a single small change to the code, only one at a time, because this is science, right? One at a time. You want to deconflate your changes. You then run your test suite, and if your test suite is perfect, it will detect, it will fail. It will say, no, something's broken. You've made a change, and your test suite will detect it. This is the ideal. And mutation testing kind of works on this basis, the assumption that your test suite catches all defects. Well, it actually helps you make a better test suite in the process. But when you get these when you don't get test failures, this is when you know you have a problem. You've made a change to your code, but your test suite hasn't figured it out. So this has ramifications for either your test suite or your code, and we'll talk about that in a bit of detail. But this is the fundamental idea. Small change, run the test suite, see if it fails, and if it doesn't, then examine your code or your tests. The basic algorithm is really simple, at least the basic algorithm as I've implemented. You have some set of operators. Operators are the things that make the small changes to your code. You have a number of sites in your code where those operators can be applied. And then, so you have this two space that you work through, operators and sites that the operators work on, and you mutate the code, and you run your tests. That's the basic idea. And you probably immediately think that, okay, this is going to result in a lot of stuff happening. And you're right, this does result in a lot of stuff happening. It takes a long time to do a full mutation testing suite on anything of appreciable size. But this is the basic idea. Very, very simple. So what happens when we run this test suite? What are the possible outcomes? There are 3 classes of outcomes when I run my test suite. One is what we call killed. This is from the research literature, really. So you've killed the mutant. Your test suite has failed, and it's failed because it has detected the change that you made in some way, shape, or form. So your test suite is performing its job. And this is good. It's properly detected the mutant. And we're going to start using words like mutant and killed and survived and stuff, and it sounds very brutal, and it is. It's kind of like a comic book, which is kind of why it's fun. Another class of results are what we call incompetent. You get a mutant that's incompetent. And these are typically cases where the modification causes your program or your test suite to just segfault or to throw an exception or do something where it just can't continue. So your test suite doesn't actually finish and give you results. It just dies in some horrible way. That's normally what incompetent mutants are like. There's a much worse class of incompetent mutants, though, and those are the ones that go into infinite loops. And we'll discuss those in a little bit. And they're difficult, technically impossible to deal with. Finally, you have the things that survive, the mutants that aren't detected by your test suite. This is what you don't want to happen. This is what you're trying to avoid. You're trying to reduce the number of survivors you have in any run. And any survivor you get means one of 2 things. And it requires your analysis to determine which of these 2 things it is, but it shines a spotlight on your code. Either your tests are inadequate, and this is very typical. None of us really in real life have perfect test suites. So mutation testing helps us identify the weaknesses in our test suites and tighten them up. Another real possibility, though, and especially on legacy systems or systems that are under heavy development, is that you've mutated some code that doesn't have any tests, and it doesn't have any tests because nobody cares about that code. It's not doing anything. It doesn't represent a feature or support any feature in your code. And so the spotlight that mutation testing shines in your code says either you need more or better tests, or you need to zap that code if you care about getting rid of extraneous code. Because code, I mean, as I think we all agree now, is it's a liability. It's not an asset. You don't want more code around. That just gets in the way of things. So you want to remove code if indeed it doesn't support any important features. So the goal, of course, is to kill all the mutants. You want 100% death rate, 0% survival rate, and so I hope by using a meme I engage all the people in the audience, right? A famous meme. Kill all the somethings, the mutants. What are the goals, then, of mutation testing? Why would you go through the trouble of doing this? The goal number 1 is coverage analysis. A lot of people already do some kind of coverage analysis where they run their test suite and they get a little checkbox by each line of code that says, this line was executed, this line was executed. And that's great. That is a kind of coverage. But that's purely telling you was the line executed. It doesn't tell you anything about whether your tests meaningfully checked the functionality or the logic of that line of code. So what mutation testing lets you do is verify the functionality, verify the logic, the meaning of that line of code. It tells you, if I've made an effectively arbitrary change in this line of code, does my test suite detect it? And that's really important. I love this graphic because it somehow communicates this sort of kind of blind, stupid optimism of, yeah, we covered all our lines of code, our test suite's perfect, when in fact, generally they're not. There's a lot of test suites just waste time because they do, execute a line of code, but don't tell you anything about the quality of your software. So that's goal number 1, and that's probably the most common goal. That's what people will think of most often when they think about mutation testing. The other one, of course, is detecting unnecessary code, what I mentioned earlier, getting rid of the code that you no longer need. So this picture, a lot of you probably recognize it, is a picture of part of the gastrointestinal system, and the important bit is down here at the end, the vermiform process, the worm-shaped process, or the appendix, right? We've all got most of us at least have an appendix. Statistically, most of us have an appendix. And when I was growing up, I was taught, that the appendix is a vestigial part of the body. We don't need it for anything. And in fact, if you go have an appendectomy and have it removed, you'll survive. You'll be just fine. And so in some sense, this is kind of what mutation testing is doing, is finding the things that we no longer need so we can get rid of them. Interestingly, kind of the twist moral to the story is, in the past few years, we're starting to find, doctors are saying, well, actually, something is kind of going on in the appendix. It's not terribly important anymore, but it actually does do something. So I guess the moral here is that when mutation testing shines a light on your code, you have to really think hard about, is it a problem in the test suite, or is it a bit of code that I no longer need? It's not always that cut and dry, and this is where your your reasoning, your skills as a developer come into play. So don't necessarily always cut out the appendix. Think about whether or not you actually need the appendix. And I like the graphic. It's kind of a cool picture. I think it's from Grey's Anatomy, so it's kind of famous. Grey's Anatomy, the book, not the TV show, which I've never watched. So what are some examples of mutations? I've talked about this notion of operators, right? Does anybody know what this moth is and why I might have it up there? It's called the pepper moth. It may have a different name in other languages, but during the Industrial Revolution or pre-Industrial Revolution in the UK, these moths were largely white, and they could sit on limestone buildings and be largely camouflaged. The Industrial Revolution comes along, burn a lot of coal, everything is covered in coal dust and turns black, and these moths mutated to be black. Almost within the span of a few generations, because the white ones got eaten, right? So it's up there because they evolved, and we kind of studied this, and it was proof of evolution, so forth, so forth. A cute picture. One typical example of an operator is replace relational operator. In this case, we're replacing greater than with less than. So we're literally going through the code, looking for greater than symbols, and swapping them out. And you would hope that your test suite can catch something like this. This is a pretty egregious change, right? You'd be surprised, but this is a typical example of the kind of thing that a mutation operator would do. Not rocket science, really, really simple things. And remember, you're doing these one at a time and then running your full test suite. So you can imagine how this inflates into a huge amount of runtime necessary to do a full mutation testing run. Another great example is break continue replacement, where you have a break somewhere in the code. I assume everybody knows what break and continue are in their language of choice, and replace it with a continue. And this is a great way to introduce, of course, infinite loops, right? A break is supposed to kick you out of the loop, and a continue says, oh, just keep on going. So this is a great way to create a mutant that is incompetent because the test suite never ends, but you can't really detect that, and we need to talk about ways to ameliorate that problem. This is the list of operators that I plan to implement for the Python implementation. And I mean, I'm not going to go over all of these. You have some sense of what they are. But you see things about like exception swallowing, so adding some code that just grabs an exception and doesn't let any of the handlers work. Things like, I think there's, super calling deletion, where you remove calls to base class implementations of functions, things like that. And okay, if you're programming in vastly different languages from Python, you'll say these don't apply to me, and you're right. A kind of a research area for mutation testing is deciding what are the reasonable operators for a given language. What applies in Lisp is not going to apply in C, is not going to apply in Haskell, et cetera, et cetera, et cetera. So these are necessarily Python specific, but some of these would apply to Java, things about exceptions and classes and so forth. But these give you a sense of what kind of operators you would face in a full-blown mutation testing suite. And you could invent your own, and we'll look at actually the implementation I've got uses a plugin system for operators. So if you have special ones maybe for a specific API you're developing, you could consider adding those into the system as well, if that makes sense for your use case. So what are the complexities of mutation testing? It's conceptually quite simple in many ways. Make a change, run your test suite, record the results. But doing this blindly and naively results in some pretty severe difficulties. Does anybody know what that is? It's the Queensland pitch experiment, and that's a filter full of pitch draining down into a jar. And a drop happens once every about 2 years. And I don't really know what the goal of the experiment is, but it's been running for a long, long time. I think the goal of the experiment is for the guy who's running it to actually see it happen. I think he's never seen it, so he always goes for a coffee break and comes back and it's dropped. Poor guy. But it represents things that take a long, long time. Pitch falling out of a funnel takes a long time. What do we do to account for this? You obviously can't be running this every day if it takes more than a day to run. One thing is that you can parallelize it as much as possible. It's an embarrassingly parallel, say that 10 times, embarrassingly parallel problem. If you have 1,000 cores, you can run 1,000 tests at the same time. You might kill your disk at that point, but conceptually, you can span it out that much. And that's all the tools that I know about do this to some degree. Mine just counts how many cores your system has and runs that many at a time. Another thing you can do is run a full baseline. You have to start with a full baseline where you run the full test suite, mutation testing suite, and get some stats from that, 5% survival rate or whatever that is. After that, you can do things like only run the tests that you think touch modified code. And that drastically reduces the test space you have to run. A little bit more easy is to only mutate code that you know has been modified or added. The reason that's a bit easier, the second one is a bit easier than the first, is this first one, that can be a bit difficult to get. I know in Python the tools for determining that are somewhat iffy, the ones I've tried at least. This, on the other hand, is really straightforward. You just look at your git diff and say, okay, at this line, this line, this line, only mutate those lines. And that will, again, drastically reduce the space you have to search through in your mutation. Neither one of these is exactly perfect, though, because you can imagine that any change you make actually changes, say, in this case, only running tests on modified code. Well, if I've modified my code, and I think I know the path through the code that a test is going to go, I might have modified that path, which means that now there's other code that I'm not testing that I should be testing, and it's iffy to go down either one of these routes. This has the same problems, but you can use these at least as heuristics to really drastically reduce the amount of time you need to do subsequent runs after a baseline. Finally, you can speed up your test suites. If you've ever seen like Dan North or any of the BDD, TDD, StarDD guys, they'll tell you need fast test suites anyways, and this is another reason so that you can do mutation testing in some reasonable way. If your test suites take 2 days, you might have other problems. So speeding up test suites is generally speaking a good thing, although it's not always possible, I admit. The second complexity is incompetence detection. You know, I mentioned that most incompetent mutants, these are the ones that just kind of segfault or just crash arbitrarily. They don't actually complete the test suite. And those are really easy to detect, of course. You just say, oh, died, incompetent, great. But then there's the class of those that potentially run forever, right? So who's that? It's Alan Turing, right? And he said, yeah, it's not really Alan Turing. That's really Alan Turing. And apocryphally, he said, yeah, good luck with that. Good luck with detecting whether or not the program you're running is ever going to end. I mean, he famously proved the halting problem is undecidable. You can't know ahead of time if a program is going to end. So you can't, in principle, take a mutant and say, oh yeah, well, he's going to run forever, so I'm just going to kill him off. You have to have some heuristic, some other kind of analysis that says, okay, he's run too long, kill it now. So the typical thing to do is you run some baseline of the test suite just over the healthy unmutated code and say that takes 10 seconds. And you say any mutant for which the test suite takes more than 30 seconds, we'll just call that an infinite loop and we'll kill it and call it incompetent. So that's the kind of strategy you have to apply. This is, again, kind of part of the researchy element of mutation testing, kind of what makes it interesting at some level and a little bit impractical. And the third complexity is what we call equivalent mutants. And okay, there's some code, and most of it you don't have to really grok. But an equivalent mutant is a mutant that is practically undetectable. When I say practically undetectable, it means that you could potentially write a test to detect mutants of certain classes, but doing so would be ridiculous. And when I go through this example, you'll understand maybe a bit better why. This comes out of the Python documentation, actually. And the function consume just takes in some sequence of things and iterates through it effectively for the side effects. That's what consume is all about. Don't worry about most of what this does. This is the important bit here. It constructs a double-ended queue and passes that iterable thing into it, and that effectively iterates through the thing as fast as possible because double-ended queue is written in C, not in Python. And the interesting bit here is at the end, max length 0. So we're saying the double-ended queue can never be larger than 0. So you're really not doing anything except forcing iteration. Now what's going to happen when you do mutation testing is the mutation testing algorithm will eventually get to this 0, and it will have an operator called constant replacement, which looks for constants and replaces them with a different constant. Now we'll replace this with a 1, or 1,000, or a -6, or something like that. And if it replaces it with 1, which is what Cosmic Ray does right now, my mutation testing tool, everything still works just fine. And the only way to detect that that's been changed to a 1 is if you can dig into your memory allocator, and not just your OS, but Python's memory allocator, and determine that an extra int or object has been allocated somewhere. And nobody has tests to do that. It's such a ridiculous test to write that you would never do it, and that's why it's practically undetectable. No, you wouldn't waste time to do it. So that's the kind of thing that's an equivalent mutant. That's a good example of an equivalent mutant. And I like this example because this is idiomatic Python. This is what you're told to do by the official documentation if you want to consume some iterable. So 3 complexities with mutation testing. So that is sort of the quick overview of mutation testing in general. And this, what we just talked about there applies essentially to every instance of mutation testing tool for every language in the world. That's the theory of mutation testing. Okay, we're doing pretty good here. The rest of this talk is about Cosmic Ray, a mutation testing tool for Python. Again, this tool is not, it's not industrial strength. It's not really ready for anything other than other people kind of hacking around on it, other hobbyists perhaps. But again, I want to get these ideas out there because I think they're kind of neat. And I'm hoping that some of you get grabbed by the ideas as much as I was grabbed by them when I saw Seb talk. And again, we're going to start looking at some Python code here, but it really doesn't matter that much. I mean, Python's easy to read, but you can hopefully kind of translate what you see here to your language of choice. The very first thing that Cosmic Ray has to do, again, don't worry about grokking all of that code, is figure out what it is it's going to be mutating. And what we do is we ask the user, please give us the name of the package you want to work against. So that's kind of the granularity. And this find modules function does all that work. The neat things in here are where the red arrows are. So let me back up a second. One of the things that really grabbed me about the whole development process of Cosmic Ray was how Python seemed to have all the bits and pieces that I need. There's a lot of things that can be really, really difficult in mutation testing. Finding the code to be tested, modifying the code, maybe having to recompile the code, running test suites dynamically, spawning things out in multiple processes, and so forth. And Python kind of made that relatively straightforward, pleasingly so. And a lot of that comes down to the kind of the architecture of how the language is put together. If you take a little diversion into software architecture, or actually physical architecture, there's a guy named Vitruvius from ancient Rome, and he wrote the thing on architecture back in the day, and he said there were three things about architecture that were important: the durability of it, effectively, the commodity of it, whether it did what it was supposed to do, and whether or not it was delightful. And yeah, I forget the Latin of it, but the delightful part is what got me here. I was continually delighted as I wrote this code to find that the hard parts had at least been thought about by the designers of the language. And I hope that if you do this kind of work in your own language, you find the same thing. Because otherwise, I would have given up. If these hard parts hadn't been written for me, I would have said it's not worth the effort. Because I'm lazy and don't have infinite time. So one thing that was really neat is this API access to the import system. So there's a keyword called import, and you give it a name, and it imports a package and binds names and stuff for you. All of that is programmatically accessible through this thing called importlib, which is part of the standard library. So I can pass it the module name, and it imports the module for me. Great. That's one really difficult thing out of the way. Now I can scan this module object for submodules, which is really all this function is doing. So now I've got the module, and I look up its path on the file system and use package util to iterate its submodules. So I don't want to spend too much time on this, except to say this was a piece of code that I was worried about writing, and I found that it was actually pleasantly simple, and I learned quite a bit about how Python does imports under the hood, which is good because I do a lot of Python training, and it helps if I know this kind of stuff, right? Yeah. The kind of next moving part is how do you run tests? This is one of the primary things, of course, that Cosmic Ray has to do. Now, there are about 1,000 different unit tests or test automation systems and packages and frameworks for Python, so I couldn't obviously implement support for all of them, so I implemented a plugin system that lets you provide an implementation for your flavor of unit testing. I have two that I provide in-house: unit test, which is or not in-house, but as part of Cosmic Ray. One is unit test itself, the standard library's unit testing system, and PyTest, which is probably the most popular one out there. But because of the plugin system I'm using, you can provide whichever one you want. If you have an in-house testing system, you can pretty trivially provide support for it. If you're using Python and you want a good plugin system, I want to give a little shout out to Stevedore, part of the OpenStack system. It's wonderful. It's a great plugin system, and it made this job very, very easy. The only thing you really have to do to implement a new one is implement a subclass of what's called test runner, and in that class implement a _run function. And its job is to just run all the tests it finds under a directory. It's really that simple. It's probably simplistic. I'll probably run into eventually some unit testing system for which this is insufficient, in which case we'll just modify the plugin API a little bit. But again, the details are not all that important, but it is an important element of any mutation system, finding the tests that are going to be run. It's something you have to tackle. This is where it gets really fun and cool, right? This is when we get into computer sciencey stuff now. ASTs, abstract syntax trees, sounds very scientific, and it kind of is. This is very technical. This is when you think about mutation testing, the kind of the meat of the problem, the fun stuff, manipulating code, manipulating your executable environment, and so forth. Python provides a module called AST, abstract syntax tree. It's part of the standard library, and it can do two fundamentally very important things for Cosmic Ray. One is it can take source code, just a string with source code in it, and turn it into an AST, give you a tree structure that you can then traverse in various ways. And it provides a set of essentially visitor pattern implementations, these little visitors called node transformers that can be made to traverse the tree and be given a chance to replace nodes as they go. And these 2 bits here are essentially how we implement the mutation phase of Cosmic Ray. We find the source code file, slurp up, read the code out of it, pass it into the AST generator, get the AST, and then traverse it and let the operators operate on the nodes as we go. And we'll look at that in a bit of detail. But this is in some sense the core, the neat guts of any mutation testing suite. So that leads us directly to what is an operator. What do we mean when we say operator? Operators are essentially the things responsible for manipulating the AST. They use the AST module to replace nodes, change a plus to a minus. You can see in this case, this is all an operator does. Given this little bit of the tree, and if his job is to replace plus with minus, that's what he does. He spits that out and shoves it in the tree, and then somebody runs the code. It's really simple to create a new operator if you want to. You just subclass from operator, which in turn subclasses from the node transformer we mentioned earlier. And you can provide these also as plugins, also using Stevedore, which again, wonderful library. They have 2 primary jobs. One is to identify the places in the tree that they're allowed, that they know how to mutate. So this guy would report when he sees a plus node, you say, oh yeah, I know how to modify that. Report it back to Cosmic Ray. And Cosmic Ray would say, okay, well, I want you to then go ahead and modify that. That's how operators work fundamentally. They're very, very simple. No single operator is really all that complex because they only ever make very, very small control changes. And typically that is to replace a node or delete an entire subtree out of the AST. This is a full example of a typical operator. Really, the whole point here is just to see that it's actually very, very small. It subclasses from operator, which is something part of Cosmic Ray. This visit unary op is part of the node transformer API, and it's given a node, and we check to see, okay, is this node an instance of unary subtraction? If so, we want to signal that this is a site we know how to mutate. And if the machinery wants us to actually do the mutation, this gets called, and the node is essentially replaced in place with a unary addition and spit back. This is the flavor of almost all the operators and all the ones I've thought about as well. I haven't implemented all the operators I mentioned earlier. Very, very simple, very straightforward, and the kind of thing you could piecemeal add to your system as you go. Now, before we get into some of the next bits of Cosmic Ray, I want to give a quick overview of how Python's module loading system works, because without knowing that, the rest of it doesn't make any sense. So this is getting into a bit of Python specifics. But it is a nice, sophisticated, pretty elegant system I found as I was researching into this stuff. There's 3 main parts. The first one is these things called finders. And a finder is just an object that when given a name, responds with yes or no, I know how to load up a module of that name. So you can have finders that know how to load modules out of zip files, off of network stores, HTTP, off the hard disk, or wherever. There's all sorts of methods for importing modules in Python, and you have different finders for each of those methods. When a finder does know how to load something, when it says, yeah, that name is something I recognize, it's supposed to spit back a loader. Now, loader is the next bit. It's responsible for taking what amounts to an empty module object, just kind of an empty shell, and filling up its namespace with name bindings, name to class, name to function, name to whatever. So the finder says, yeah, I know how to do something with that import. The loader does the actual work of filling up the namespace. The last bit is this thing called systemapath. And systemapath is just a list, literally a list, of finders. And when somebody in Python says import foo, Python goes, OK, first finder, do you know how to import foo? No? OK, next finder, do you know how to import foo? Goes down the list until somebody says yes. And if nobody says yes, then you get an exception. You can't import that. So all these put together basically give you complete control over how the import keyword maps the names it gets to the things it actually does. And this is what we need complete control over to make the tests work, to make mutation testing work. Because the test suite themselves, we never modify. The test suite need to be able to say import foo and get mutated foo when we want mutated foo to be in place. And so we need to have fine-grained control over this entire chain. And so that's what Cosmic Ray does. The first thing we implement is a finder, of course. And the finder does nothing more than associate a name, a module name, with an AST, a mutated AST. So we, as part of the algorithm, take the pristine AST, mutate it in some way, create a finder that binds the module name to that AST, and stick it up in sys.metapath. So that when a test says import that module, it gets the mutated version. This struck me as really kind of neat and elegant, and kind of a present with a little bow tied on top. It just felt really nice when this all started working. The code is incredibly simple. This is all of it right here, minus documentation, of course, which I have copious amounts of because I'm a good programmer. The only thing that you really need to understand is that find spec is what Python calls when it's asking for whether this finder can load the module. And we just say, is the name that they want equal to the name that I've been given? If so, pass back the AST right here in the context of a loader. No big deal. This is really, really simple. And the fact that it was so simple, it gives you the sense that the designers of this system really thought ahead. They probably didn't think about mutation testing itself, but they didn't think too narrowly. They really thought broadly about giving programmers at runtime full control over the guts, the machinery of the language itself. And this is what we're getting into, really the guts of how Python works at TOTO. This is the bottom basement of how Python works, except for a bunch of C code, which, come on. The next bit is loaders. So the finder, when it recognizes a name, spits back a loader. And this loader, all it does is take the AST object, compile it into a code object, and then execute that code object in the namespace of the module. Okay, that's a bunch of verbiage. Basically, it just fills up a module thing for you using the mutated AST. Oh, again, super, super dirt simple. This is the entire implementation, minus again comments, of the AST loader. And you can see this is kind of the magic of the magic down here. We have the AST, some mutated AST. We compile it. This produces a code object. We execute that code object in the namespace of the module that's passed into us. And that gets bound to the module name in the caller's context. And this is how the tests get access to mutated ASTs. And this, yeah, again, this is the kind of warm, fuzzy feelings I get when I think about this code and how kind of pleasant it was to write it. What a neat project it was to get to work on, because I didn't have to do a whole lot of work. And I got a neat tool out of it. There's some other bits and pieces that are not too Python specific. They're things you'll need to think about if you end up thinking about mutation testing on your own. One is sandboxing. Potentially, a mutant can do all sorts of wacky things. Like the mutant could start doing things like manipulating sys.metapath, or deleting files, or sending pings to an orbiting space station. Or you don't know what it's going to do, right? Because you've mutated it. It's probably not going to ping a space station. But I mean, we got rocket scientists here, so who knows? Basically, though, you want to avoid what I call cross-mutant interference, the potential that they can influence how each other works and therefore pollute and corrupt the output from your testing. So there's this library called multiprocessing, which has a kind of a threads-like API that lets me actually spawn out processes in a very simple way. And that's how I do sandboxing. Each time I do a run, for each mutant and each test suite pair that I have, I create a separate process to run that. And that way I can guarantee that nobody is stomping on anybody else's namespace, nobody else's module space, or anything like that. It's a bit heavy-handed and a bit of a hack, but it works, or seems to work really, really well. And I'm comfortable that it's doing the right thing, at least until somebody tells me otherwise. Pika. This is very Python specific, except, well, Pika is an actor model implementation in Python. Is anybody here, I mean, if you're a Scala programmer, I guess you probably, who knows actor model at all? You should all know actor model. I mean, this is one of the most important things, in my opinion, that we should all be thinking about. It's a great paradigm for developing programs, especially programs that can take advantage of massive, parallelism and all the cores we've got available nowadays. Actors they're simple to think about, they're robust, they scale out really well, they scale up really well, they're proven mathematically. You can read some fascinating books on actor model theory. There's one called The Black Book by a guy named Gul Aga from MIT Press, and he explains actor model theory in terms of general relativity and things like that. And it's just really fascinating to read it, and you come away thinking, yes, this is the answer. It really is. But for me, actor model stuff, it really simplifies design. It simplifies the cognitive space that I have to work in as a programmer. Because I don't have to think about things like locks and threads and so many race conditions and all these things that if you're doing thread programming you have to worry about. It all just disappears because it vastly simplifies the model you're allowed to work with without really binding your hands too tight. So I really suggest looking into it. The benefits I see from it, how much time do I have? Okay, 10 minutes, good. Is that these mutant testers, each of these are my actors that are actually running the tests. So each of these is responsible for launching a process that then runs the tests. And I just make as many of these actors as I need, and they each feed from this thing called the process queue, or the queue manager actor. And they just pull the next bit of work to be done off of that queue, and they do it. And there's no way they can interfere with one another. All they can do is talk these little messages. And I could scale that out just by creating more mutant testers. If I have 16 cores, I create 16 mutant testers. On this, I only make 4 or 5 or whatever the number is. I've seen this pattern over and over again, that you start with some program that has some inherent concurrency in it, and you try to code it up with threads or some other paradigm, and then you step back and you go, this is a real mess. This really ought to be simple, because conceptually it's very simple. And then you apply the actor model to it, and your code becomes simple. It becomes something you can reason about, something you can test much more easily, because testing actors is trivial. You just instantiate the actor and throw messages at it and see what messages come out. That's the only thing actors can do, so they become really easy to test. And they're really robust. And I can go on, but I'm running out of time. So look into the actor model. Whatever language you're using, whatever stuff you do, it's really, really important, I think. And it's fun. It really is fun. Finally, I use a feature in Python called asyncio, a relatively new feature. It's just an event loop that's designed to support high-performance concurrent I/O. And I just have this event loop sit in a loop, checking the testers. And he says, are you all dead? Are you all dead? Are you all dead? And once they're all dead, the program is done. So this is really a Python implementation detail of how do we determine when all the actors are done. But if you're using Python, you should be learning about async I/O, because it's the future for many, many things, for event-driven programming, reactive programming, that kind of stuff in Python. Right, so how does this all sort of fit together? The first thing that Cosmic Ray does is figure out which test runner it's going to use, unit test, PyTest, whatever. It's a command line option that the user passes in. It then figures out the modules it's going to mutate. It scans the package directory. It figures out all the operators it's going to use, because of course the operators could be provided by external plugins. It then lazily generates a sequence of mutated ASTs. And the lazy is important, because if you try to generate the full sequence, it would be really, really big, and there's no reason to have it all in memory at the same time anyway. They just get generated as the mutant tester actors decide they need another one. They go, hey, give me another one, give me another one, give me another one. And the queue manager is responsible for essentially cranking those out as they're needed. And then for each mutant, we run the tests. Each test runs in a new process, and each manipulates its local sys.metapath in its own process. And this is really important to make sure that, I mean, this is the sandboxing here, that each process has its own sys.metapath, and that's critical. If they all shared a sys.metapath, there would just be complete chaos. And figuring out how to do this correctly it was complete chaos for a while. I was losing my mind. Excuse me. All right, that's about it. I could do a quick demo, but it's really just me on the command line kind of showing you how the program runs. I think maybe it's better use of time to take questions. So if anybody has any questions, now's the time. And I can do a demo later, like after if anybody wants to see it, I'm happy to show you. Before we do the questions, let me just say, remember to rate the session. And the only important button is the great smiley face. And thank you. Yeah. Have I thought about using AST manipulation for other things? Not really. I mean, it is a general. The question was, have I thought about using the AST module for things beyond mutation testing? Not really. I mean, it is a general purpose tool. It's not mutation testing specific in any sense, and it's kind of a cool thing. If you want to do code generation and stuff like that, you can certainly use AST to do that. But I don't have any plans right now to use it for anything else. But if you've got neat ideas, it's an easy module to use. So yeah. Right. The question was, are there any other tools, mutation testing tools that I know about? The only one that I know about is called PIT, or maybe it's pronounced PIT, but it's a Java tool. It's apparently full-featured, robust, industrial strength, ready for use. It's got a lot of fans and a lot of users, and a really smart guy behind the project. I think it's pitest.org, maybe is the name of the URL, but it's PIT mutation testing Java. Google that and you'll find it. It is, it's apparently a great tool, and just kind of light years beyond anything else that's available right now. Yeah. So the question was, have I thought about how to assist the users in interpreting the output that they get? Because the mutation testing just kind of shines a light and says, okay, this test failed, or this test, or everything passed, and blah blah blah. Typically, when you get the results, like out of Cosmic Ray, the results tell you the line that was changed, and it tells you the nature of the operator. So it's pretty easy to figure out what was changed. And so it's not always all that difficult. to figure it out. What could be really difficult is to figure out sometimes if what you've got in is an equivalent mutant that you can ignore, or if it's something you really have to worry about. Because you could imagine situations where you replace greater than with greater than equal. That's a pretty small logical change, and it can actually be impossible in like C++ in a private method to actually test that in a direct way. So I guess to answer your question, I haven't thought too hard about providing assistance because it seems that just having the location of the change that survived is typically enough. And beyond that, you would have to have a really, really smart system to be able to assist beyond that, I think. I had something else I was going to say, and it's flown out of my brain. I apologize. Okay, the question, what's a typical failure rate, or a typical survival rate? I don't know. I would feel like I'd be lying if I told you there was a typical number, but on the tests that I've run, I see everything from 100% mortality rate, which is what you want, and that's a really good test suite, but typically that's on small projects, to if you got a poor, and this means kind of typical test suite, you could have a really, really high survival rate, like 90+%, because test suites are not that sensitive, it turns out, very often. One thing that I puzzle about and ponder about in the wee hours of the morning is how much, if mutation testing takes off and becomes a more popular tool, will it start to guide the way we write tests? I wonder about that because things like equivalent mutants and stuff, well, if we worry about those, that might modify the way we write our code to make it more testable in a mutation testing sense. And is that a good thing or a bad thing that this kind of arcane testing system is forcing us to write code in a certain way? And I've gone off on a bit of a tangent there, but there's not a number I could give you. It really depends heavily on the kind of code you've got, the number of tests, and the quality of your test suite. A related interesting question, and one that I don't have an answer to, but I hope somebody someday figures out, is how much language determines the efficacy of mutant testing. If you talk to Haskell aficionados, they will tell you that, of course, Haskell is the perfect language, and if it compiles, it works. And mutation testing should not even be necessary. Or Ada users might tell you the same thing, that the code is so tight that any mutation is going to cause things to just collapse. And I'd be interested to see research into that area, just on a sort of personal level. Yeah, the question was, how is this related to sort of standard code coverage analysis? It's like code coverage analysis on steroids. Standard code coverage analysis, most tools will simply tell you, okay, I've run my test suite, and every line of code was executed. Whether that line of code did the right thing, or whether our test suite is sensitive enough to tell us that we've broken something. I mean, because a mutation is just a stand-in for yeah, that's a good question. I mean, generally, the follow-up was, is there a good reason to use one over the other? Coverage analysis tools are generally much faster, so there's a reason to use them. But I wouldn't wait to get 100% coverage with a standard tool and then start using mutation testing. I would maybe use them in parallel. They can work together because often coverage analysis tools also tell you which tests exercise which line of code. And if you want to use that information to reduce your mutation testing space, on a per change basis, that can be really useful. So they can work in tandem, I suppose, in that way. Yeah. Yes?
You say that you only modify one small thing and then run tests.
Yeah.
Is that because it doesn't make sense to modify multiple things, or just to take too long to get all?
The reason you do that is so that you can be guaranteed that the results, you know which change caused the failure in your test suite. If I change 10 things at once and then my test suite starts to fail, I was left scratching my head going, well, which change?
Yeah, but I was thinking just doing that on top of changing one thing, changing multiple things to see if that would...
So doing some kind of binary space reduction, like doing a bunch of tests, and then if we get a failure, then only half, and then only half, or something like that?
Yeah, maybe.
Yeah, that's a good question. I'm sure I've thought about this to some degree, and concluded that doing one test at a time is the way to go. And maybe there's a mathematical reason for that. But I think the ultimate explanation is it's the scientific way. Only change one variable at a time. But I guess in the end, if you're not too concerned about conflating mutations, like maybe I have one mutation that made on its own would cause a failure, but then if it's made in change with this guy, then there's no failures, and all of a sudden you're really confident in your code, but in fact it's crap. Yeah, you don't want to be in that position. Yeah, so the question was, could we speed things up essentially by reducing the scope of the tests we're running? And I suppose that would be a refinement to the way Cosmic Ray runs now. You could say, instead of testing a whole package, test just this class. I think that's reasonable. But since it's generally your test suite's responsibility to insert the mocks and stuff, you get all that for free when you test the class. It's not some new responsibility of the mutation testing suite. But yeah, they can work in concert very well. Okay, thanks again, and if you want to talk about this later, just grab me in the halls. Thanks.